Hello and welcome back to another LeetCode problem. Today we're going to be doing number 877 Stone Game. And we have actually done Stone Game 2 and Stone Game 3 on the channel, so I'd encourage you to take a look at those. This is going to be kind of similar to those. And so let's have a read. So Alice and Bob play a game with a pile of stones. There are an even number of piles arranged in a row. Each pile has a positive integer number of stones. The objective of the game is to end with the most stones. The total number of stones across all piles is odd. So there are no ties. Alice and Bob take turns. Alice goes first. Each turn, a player takes the entire pile of stones, either from the beginning or from the end. This continues until there's no piles left, at which point the person with the most stones wins. Assuming Alice and Bob play optimally, return true if Alice wins or false if Bob wins. So let's look at first example. First example is we have 5, 3, 4, 5. Okay, Alice starts first and can only take the first 5 or the last 5. So if you think about it, if Alice takes, so the biggest number is actually 5, so it doesn't really matter. In this case, I believe. I think either way, she's gonna win no matter what. But yeah, but let's just so let's actually look at like the ways this game can be played, right? For this example, so say she takes from the first pile. So if she takes from the first pile, then, so she has 5, and then there are 3, 4, 5 left. And then if she takes from the second pile, she also has 5, the last pile I mean, and there are 5, 3, 4 left. Okay, now Bob takes. So obviously Bob is going to want to take the most. And so here, so I'm just going to only have one thing because Bob is just going to want to take 5. So then Bob takes 5, and we're actually not going to include Bob's score, and I'll show you why. Then the pile is 4, 3. And in this case, Bob is also going to take 5, but now the pile is 3, 4. And then next, Alice is obviously going to take the 4, so it's 4 and a 4. And so Alice's total score is going to be a 9 here. The reason we don't need to calculate Bob's score is because we have a total, right? So this total is actually 17. And so if we know Alice's score and we know the total, we can easily get Bob's score because it's Alice plus Bob at the end equals 17. And so Bob is going to have 8 here no matter what happens. So Alice is going to win this one. But you can see like how you want to pick the left or the right. And let's look at the other one. So 3, 7, 2, 3. Let's take a look at that one. And let's see what choices Alice can make and whether she wins or not. So let's say Alice takes from the left. So it's going to be 7, 2, 3 left. Alice takes from the right. Her score is going to be 3. And there is going to be 3, 7, 2 left. Okay, so now Bob is obviously going to always take the 7 here. There's no other better move, so we're just going to only show that branch of the tree. And then here, Bob is obviously going to always take the 3. So there's going to be a 7 and a 2. And then, so in this case, Alice is obviously going to take a 3. And there's just Bob to finish off with a 2. And then Alice is going to take a 7 here. So what did Alice take here? So she took a 3. Yeah, she took a 3. And she took a 7 here. And so here she took a 3 and a 7. Here she took a 3 and a 3. So this 3 and the 7 wins if she can get there, right? So that's what she'd want to do. She'd want to take this 3 first, because then we have this 3, 7, 2 left, and then no matter what Bob takes, the 7 is going to be exposed, and she can take the 7. And so that's going to be a yes. She's going to win because she's going to have a score of 10. Okay, so you can kind of see from this problem, Alice is trying to maximize her score, and Bob, since this is a zero-sum game, for Bob to win, he needs to minimize Alice's score, right? And so at every state, we need to have like a left and a right index. This is kind of similar to my other video for the other stone game. And then we need to have whose turn is it, right? And so this is going to be a dynamic programming problem where on her turn, she's going to want to maximize her total sum starting at whatever index. So let's say, this is the L and the R. She's going to want to maximize her result. And then what Bob is actually, he's going to want to take something to minimize the result after he takes something, right? So if we have something like this for Bob, let's say Alice takes something, Bob is going to want to take, let's say he takes this, he's going to want to take whatever minimizes the next result, right? So whatever the DP in the next state is. And so that's kind of what's going to happen is Alice is going to try to maximize her DP, whatever state she's in, and then Bob is going to try to take something to minimize the next DP after that take. And so that's what we're going to actually do. And then what we can actually do is we can try to maximize Alice, and we can have Bob try to minimize Alice, and then we can return the maximum value there. And then once we get the maximum value there, it'll be some number of stones, right? We'll call that A. Then we have a total. So then total is A plus B. So we have a total, we have an A, right? We can calculate a B, and then we just see is A greater than B. There are no ties. So it's either going to be yes or no. And if it's yes, then Alice wins. So that's how we're going to do it. So let's code that up. And we are also going to have, so by the way, how many states do we have? So we have a left, we have a right, and we have a turn. So those are the things we're going to need in our visited dictionary for this. So let's do that. So we're going to have a visited dictionary as always. And we're going to have a dynamic programming as always. We're going to have a left, a right, and a turn. And now what are our base cases? So our base case is if we can't take anything else, and that's going to be if our left is greater than our right. So we're going to update our left and our right, right? So like, let's say we have this 3, 7, 2, 3. Let's just say like they start here. Let's say we take from the left, so we would update the left here. Let's say we take from the left again, we would update here. Let's say we take from the left again. And then at a certain point, the left and the right are going to be the same. And then when you take that, we're just going to move the left to be greater than the right. So when the left is greater than the right, that means we have no more values to take. Okay. So if left is greater than right, that means we have no more values to take, and so we can't take anything else, so we just return 0 there. Then we have our other base case where our step is in visited, so left, right, turn, visited. And the nice thing is also, so these piles lengths are only 500. So even though this is going to be like an n squared solution, it's okay because it's only 500 squared. So that's another thing you want to look at the constraints. Like if this was 10 to the 5th, then that would give you a hint that you can't have an n squared solution. Okay, so left, yeah. So return. Okay, so now we're going to have two different cases, right? So if it's Alice's turn or if it's Bob's turn. So Alice is going to try to maximize her result. So if we're trying to maximize, let's just say for Alice it's going to be turn is 0, and for Bob it's going to be 1. So if turn is 0, then what are we going to want to do? We're actually going to have a res here. So we're going to, if it's Alice's turn, we're going to want to maximize for her, right? So if we want to maximize, then we want to start with a result that's negative infinity. And we're guaranteed to have something in here, so we don't have to worry about like returning negative infinity, I think. Okay, otherwise, if it's Bob, he's trying to minimize the next result, right? And so if he's trying to minimize, let's make the result infinity here. Okay. So the same thing for the DP now, we need to, so we can either only take the left and the right, those are our only two choices. So we're going to try to maximize. So this is the same thing. So if, we could technically just write it in here if we want to. Yeah, so let's just do that. So if it's Alice's turn, res is negative infinity, and we're going to want to maximize that, right? So actually, do we need this to be? No, because we can only take the left or right, so we don't actually even need this. We can just say maximize. So we either take the left or the right. So let's try to take the left. So the left would be piles left plus DP. We need to update our left, right, and then we need to update the turn. So that's going to be 1. So that's for Alice. We take the left. And now we also need, we need the other way, right? Yeah. So we need to take from the right side. So that's going to be similar, except this is piles right. Plus DP, now we need to, so this is going to be right minus 1. We're either going to be upping the left or making the 1 go back 1, the right go back. Okay. And that's going to be, why did I have a 1 again? Right, because it's Bob's turn, right? So if it's 0, yeah, okay. So now, actually, we don't even need this res because we're only going to have one. We're only going to have one thing here, so we can just write this in directly. Okay, and then here, remember, we're trying to minimize Alice. So that's going to be, if we take, so if, and we also don't need to add here, right? Because when it's Bob's turn, Alice isn't going to get any stones, kind of like in my other problems. So Alice is actually going to get no stones here, but we're trying to minimize her next move for Bob if he plays optimally. Okay. Because yeah, I think they both play optimally, right? So let's see. Yeah, assuming they both. Okay. So Bob is going to minimize. So let's say he takes a left. That means this is going to be left +1, right? And now it's going to be Alice's turn. And now if he takes from the right, that's going to be left, right, -1, 0. Okay, now we can simply return this. Okay, so now what we need to do is we need to get a score for Alice. So let's just say that's going to be Alice equals dp. So the left and the right are initially going to start at 0, and then the last element in pile, so that's like pile -1, and then it's going to be Alice's turn.
Okay, so now we need to do Bob, and it's pretty straightforward. So remember, this is a zero-sum game, so Bob is just going to be the total minus Alice. So Bob equals Alice minus Alice. And then we just simply have to check if Alice wins by saying, does Alice have more tiles than Bob? So, and there are no ties, so we don't have to check for that. So let's take a look. Okay, and so let's think about the time and space complexity. So for time here, we can have pile states for left and pile states for right. So let's call the length of piles n. So that's going to be n squared. And then we can have 2 for turns. There's just going to be like 2n squared, which runs down to n. And then for space, it's going to be n squared as well. So yeah, so that's going to be the time and space complexity. And yeah, for time, it's going to be n squared because we can have n squared states. So that's going to be like the worst case, what we have to do. Okay, and I think that's it for this problem. So if you liked it, please like the video and subscribe to the channel. And I'm going to link this in the playlist with the other stones. And I'll see you in the next one. Thanks for watching.